So I just want to spend a little bit of time at the start of this lecture to finish up on the between subjects ANOVA, and also to talk about kind of at a high level theoretically and mathematically what the difference between a between subjects ANOVA and a within or repeated subjects ANOVA. Now we've already talked about these differences in reference to the t-tests, and again just recognize that when we move to repeated measures design within subjects design, and those two terms are interchangeable. What we're referring to is that the same participants are being exposed to each level of our independent variable. So whatever, if we have three or more conditions, the same people are being exposed to all three of those conditions. And what that allows us to do is to focus on to basically ignore the individual differences. We don't have to calculate those or even necessarily include them in the equation anymore, because we can focus on the actual differences between our conditions, because we're no longer having to make an estimate of how the groups differed, because they're not differing. They're effectively the same people. Now also remember that we can use the repeated measures or within measures design if we're using matching, but because the technique assumes that the people are the same in each group, in fact it assumes that they're literally the same people, if we are using different people that are matched, we want to take extra care in the methodology we use and the rigor we use to ensure that that matching is successful. I also do want to take a moment to also thank everyone that actually submitted pictures of your Halloween costumes. And if you haven't had a chance, I would suggest you go to that discussion and take a look at all of the creativity that was displayed there. Okay, so let's start talking about, again, finishing up on the actual between subjects ANOVA, what we talked about last week. So again, the between subjects are independent measures ANOVA, and again, between subjects or independent measures is used fairly interchangeably. Has our mean squares between as the top of the equation, the mean squares within at the bottom of the equation. And again, these are calculated from the sums of squares between, representing the effect size, divided by the degrees of freedom between. And at the bottom, the sums of squares within, representing pretty much all of the variance across all of the conditions, again, divided by the degrees of freedom within. And those degrees of freedom, again, is the between, the top of the equation, is k, the number of groups or conditions, minus 1. And the bottom of the equation is n, the total number of participants across all conditions, minus the number of conditions, k. And how we report this, again, is an italicized f, parentheses, the degrees of freedom between, comma, the degrees of freedom within, parentheses, equal the actual test statistic, and again, the p-value. And if that p-value is less than 0.05, we would also report an effect size. And we're going to talk a little bit about the effect size of the independent measures ANOVA in a slide or two. If we're looking at SPSS, here's where we're getting that same piece of information. So when we're looking at SPSS, we're going to skip the corrected model and intercept. Though there are some reasons to occasionally look at this, especially if you're not getting the results that you want, it's generally not information that we're necessarily interested in. What we're interested in is the actual line, usually the third line, which is actually labeled by our independent variable, in this case, study type. And we're going to get our degrees of freedom between, we're going to get our mean squares between, and we're going to get our F ratio, our significance, and our effect size, which in the case of an ANOVA is generally going to be partial eta squared. The bottom or fourth line is the error line, and again, that's our sum of squares, our degrees of freedom within, and again, our mean square. And again, the F ratio is simply the mean squares of our IV divided by the mean squares of our error. So this is how we're getting that information from SPSS. And just a brief word on effect size. There are different effect sizes that we can use with ANOVA, and we're going to get into a little bit of some of those other ways that we can look at effect size depending on the complexity of the model next semester. But for the purposes of what we're doing in this class and the type of models that we're looking at in this first semester, we're almost exclusively going to be using the partial eta squared. And I have at the bottom of the slide kind of the general rule of thumb. A partial eta squared of 0.01 is small, 0.09 is moderate, and anything over 0.25 is large. And partial eta squared is effectively a measure of variance explained. So again, how much variance we're explaining. And I want to stress again that though a partial eta squared of 0.09 means we're only explaining 9% of the variance. In other words, our independent variable is affecting our outcome, but it's only affecting it about 9%. In other words, 91% of that outcome is being affected by other things. But that's still better than if we had no information or no predictive qualities. So 9% is an increase in our ability to predict above and beyond just chance or just guessing. And if it's significant, we at least can say that it's very likely there is a relationship, and having this information can inform better decisions, but also recognize that you should kind of moderate the decisions you make on data based on the effect size. So again, a 9% increase in your ability to predict which condition is going to result in a better score may inform a fairly cheap decision, like using a study guide. However, if the interventions that you're looking at cost millions of dollars and the outcome is very small differences in an organization that does not result in millions of dollars of more profit, 9% may be significant, it may be interesting, but it may not actually have utility or be meaningful. So make sure that you're not getting lost in the numbers, that you're not just going, if it's significant, it's meaningful. If it's meaningful, it should be used. So we want to recognize that there is legitimate limitations in how much of human behavior we can predict in any kind of psychological model, and that's why a 9.09 partial eta squared, 9% of variance approximately described or explained, is considered a moderate effect size. And if you're explaining a quarter of behavior with some kind of intervention or IV, that's a pretty large effect size, but that also still represents a large chunk of variance that is not being explained by your independent variable. Now, as we move to the repeated measures, and the rest of this lecture is going to be focused on the repeated or within measures design, we have a very similar situation. We have the mean squared between, and again, it's going to be sums of squared between divided by degrees of freedom between. However, how we're getting the sums of square between is a little different. And then it's going to be divided by the mean square of error. So notice we've changed that term. We're looking at sums of square error and degrees of freedom error. And the reason we've changed the term is that in the independent model, or the between subjects model, the bottom of this equation was mean square within. It was all the variance between your conditions. In this case, it's only the error variance we're looking at, because we're actually not calculating or estimating individual differences, because we're assuming there are none. They're the same people, or they're highly matched. The degrees of freedom for the top of the equation also stays the same. Number of groups or conditions minus 1. However, the bottom does change. It's now number of groups minus 1 multiplied by small n minus 1. So if we have 10 participants in 6 groups, that would be a k of 6 minus 1 is 5. And we have then 10 participants in each group, minus 1 is 9. So that would actually be 5 times 9. The degrees of freedom would be 45. So that's how we're actually calculating the degrees of freedom error, and it does change if we're doing repeated measures. How we're going to report it, however, does not change. In other words, the statistics don't tell you if it was a repeated measures design or an independent measures design. You have to tell the reader before you ever present the statistics what specific test you ran. If we're looking at SPSS, it's going to look a little bit different, but we're still looking for the two lines, basically the top line and the bottom line. In this case, the top line is going to actually be the very first line presented in SPSS. It's going to give us our sums of squares, our degrees of freedom, and our mean squares. And again, it's also going to give us our actual statistical test. It's going to give us that F, the significance, and the partial eta squared. The bottom of the equation, the error, is going to be, again, the first line of that second block. And in this case, we again see that we have a sums of squares, 33,618.867, and a degrees of freedom error, 58. And again, the F value is that mean squares of your effect divided by your mean squares of error. And again, in this case, we can see our F is 13.611 with a significance of 0.001, which we would report as less than 0.001. We never report a significance of 0. And again, we have that effect size, partial eta squared of 0.319. So that's above 0.25. This is a large effect in this particular example. And again, we're going to get that same information, and we're going to report it the same. Now notice that we're taking the line that says sporicity assured, and we'll talk about that a little bit as we move forward. There is an additional assumption of a within subjects ANOVA that there is sporicity and that it has occurred. If we find that we violated sporicity, we need to use, again, an adjusted value. And there's 3 different ways to adjust those values, and we will be talking about that at some point. So let's talk theoretically and mathematically about the difference of a repeated measures ANOVA versus an independent measures. Now this page, this slide is not based on any of the previous examples, but it is based on a real data set. And what I did with that data set is I ran it through a independent measures analysis and I ran it through a repeated measures analysis. In other words, remember again, SPSS and statistics don't know what's going on. They're just crunching numbers. And theoretically, we have the bottom here. At the bottom of this slide, we have the theoretical what's happening. That theoretically, on an independent measures or between measures design, the top of the equation is the between treatment effect and individual differences and error. And the bottom of the equation is just the individual differences and experimental error. So if we look at it, we're basically adjusting for both error and individual differences, both on the top and the bottom of the equation. And the only thing that makes the top of the equation different is that's where we put any actual treatment effect. If we look at the red box at the bottom, this is what's happening theoretically with the repeated measures ANOVA. We have the between treatment effect just like we did originally, but we also have the change difference. In other words, we're actually getting to add the effect or the treatment effect twice on the top of this equation. We're replacing individual differences with how those individuals differed from group to group to group. So not only are we getting the between treatment differences, what were the mean differences between each treatment, we're also getting to add in how the various people changed from condition to condition. It effectively allows us to double up on looking for an effect. And we still have experimental error. And the bottom of the equation is change difference and individual and experimental error. So theoretically, what we're looking at is a little bit different, primarily because we're replacing individual differences with change differences. Now let's look at what that looks like mathematically. So if you look at the between, which is the blue line, and the independent measures, which is the red line, as far as the top of the equation, you'll actually notice the exact same data does give us a smaller number for the top of the equation when we're looking at a repeated measures ANOVA. The degrees of freedom didn't change. The mean squares, however, did. What really happens, though, is though we get a small decrease generally in the effect size or the number at the top of the equation when we run a repeated measures ANOVA, we get a much smaller number as far as the bottom of the equation because all of that individual difference is no longer there. It's just experimental error and a little bit of change difference. So that's where we see that red line gets much, much smaller. And this is what makes the repeated measures ANOVA a more robust or stronger test, a test that finds differences much easier. So again, looking at the exact same numbers and exact same data, running it through as an independent measures ANOVA, I got an F of 9.38. Running it through as a repeated measures ANOVA, I got a 14.47, a much larger number. And that's usually going to occur no matter what. So, generally speaking, if we're looking at the same data, we're almost always going to get a stronger effect when we use a repeated measures ANOVA. Now, we wouldn't be using the same data in reality. If we have a between subjects design, we use a between subjects ANOVA. If we have a repeated measures design, we use a repeated measures ANOVA. This is more of just helping you understand why there's an advantage to using a repeated measures ANOVA. It gets rid of the estimates of individual difference, and it's a much more likely test to find a difference if it's there, and to let you confidently claim that it is a significant difference.